Did you get it? Did you got the previous recording?
Yes.
Okay. Okay, so you can see the slides, and let me just remind you where we were last time, yesterday. And after the break, we're going to talk about the project a bit. Okay. Last time we talked about we were doing I was refreshing your memory about what you need to know so far, and we talked about hypothesis testing via test of significance approach. Can somebody remind me, when we say test of significance approach, what do we mean? Test of significance approach, what do we mean? Test of significance approach, what do we mean? Is t-statistic and p-value. Okay. T-statistic and p-value. And confidence interval approach, we construct a confidence interval. Okay. So the probability distribution of the estimators now, you know, our estimate alpha hat would follow the normal distribution with a mean alpha and the variance of alpha, and beta hat would basically do the same. Okay. Now, the test of significance approach, what we need to do in step 1, we need alpha hat, we need beta hat, we need the standard error of beta hat, we need the standard of beta hat, and the test statistic is based on this ratio, where in the denominator we have the estimate beta hat, minus the value of beta under the null hypothesis. Now, a very specific and important case is when beta equals 0. When beta equals 0, the t-statistic is beta hat divided by the standard error of beta hat. Okay. Now, who is going to tell me, who is going to help me why beta hat is an important case? Why beta hat is an important case? Why beta equals 0 is an important case? Why beta equals 0 is an important case? Why beta equals 0 is an important case? Who is going to help me with that?
Because it means that the variable, the independent one, is not significant for the dependent variable.
Very good point. Who was talking?
Salvatore.
Salvatore, very good, Salvatore, thank you very much. So when we are testing whether beta equals 0, in fact, what we are testing is X cannot help me in explaining Y. One more time, this is important, I'm going to repeat it. What it does, it helps me to answer the question whether X can help me in explaining Y, whether X can help me in explaining why. So when I'm testing whether 0 is a value, 0 is a possible value for beta, what I'm testing in fact is whether X can help me in explaining why, whether X can help me in explaining why. Okay. Whether X can help me in explaining why. So beta equals 0. In fact, I'm asking whether X can help me in explaining why. Okay. So we're going to do this choosing the level of significance, and we have 3 levels of significance that are important. This is the 5%, the 10%, and the 1%. Now Gretel automatically gives 2 stars when something is significant at the 5%. It gives 1 star when something is significant at the 10%. It gives 3 stars when something is significant at the 1%. Okay, let me remind you here what we did yesterday in Gretel. I'm going to show you later. I'm going to show you later what we did in Gretel. So in the end of each coefficient, we have the number of stars, and we see whether a coefficient is statistically significant. I'm going to repeat it one more time because this is very important. When a coefficient can take the value 0, then the variable that is attached to this coefficient does not help me in explaining why. It does not help me in explaining why. Okay. The variable that is attached to the coefficient does not help me in explaining why. So it is very important to see whether a coefficient can take the value 0, because in effect I'm testing whether the variable that is attached to this coefficient is important or not. Okay, now we have a rejection and non-rejections area. So here we have 0, and usually we have this is 0, and usually this is 1.96 here, 1.96 here. Okay, so we have the level. Oops. This is the case for the normal distribution, and these are the 2 tails. Okay. Now we can do the same type of test one side if I want to see whether something is strictly positive or strictly negative on the other side. And we perform the test. If the test statistic lies in the rejection region, then you reject the null or you do not reject the null. So you can say reject the null hypothesis, or you can say you do not reject the null hypothesis. Okay. You should be familiar with the normal distribution and the characteristic bell shape of the normal distribution. We usually scale the normal variate to have a 0 mean and unit variance. How do we do that? We subtract the mean and divide by the standard deviation. In fact, we are also using the t-distribution a lot, and there is a specific relationship between the t and the normal. The t and the normal are both symmetric and they are centered around 0, but the t-distribution has another parameter, which is the degrees of freedom. The t-distribution we employed when do we employ the t-distribution? Who is going to help me? When do we employ the t-distribution?
To test the significant difference between mean in case of a small sample.
When do we employ the t-distribution? When we have many observations or when we have few observations?
A small sample.
When we have a small sample. That's good. So we usually, when we have a relatively small sample, What does a relatively small sample means? We don't know. Okay, so what's the difference between the normal and the T? The T, you can see, has fatter tails. Okay, the T has fatter tails. Okay, the T has fatter tails. So one important difference between the T and the normal is the fact that the T has fatter tails. Okay, fatter tails means what? Could somebody help me? What does fatter tails means?
It is less precise.
It is
Less precise because the variance is more.
less precise, that the variance is more. When we say fatter tails, what do we imply?
I think large rejection region.
Yes, but fatter tails means what? It means that
That
extreme
there are-
values are
More dispersed.
yes. So somebody wanted to also say something. So fatter tails, what does it mean about extreme values? Fatter tail means that extreme values are more frequent compared to the normal distribution. When we say extreme values, we mean values that are far away from the mean. So fatter tails means extreme values are more frequent than the normal. Okay, what does extreme values mean? Extreme values means that, you know, when you have, for example, -4 or -5 or +4 +5 is more likely to happen than the normal distribution thinks. It is more likely to happen than the normal distribution thinks. Okay, so the tails, when we say tails, we imply what is happening in the extremes. The tails implies what is happening in the extremes. Okay, any questions so far? Okay, is this clear? Okay. So the T and the normal, well, the normal has a specific set of critical values. The T distribution does not have a specific set of critical values. The critical values of the T distribution depend on what? The critical values
Degrees of freedom.
It depends on the degrees of freedom. So how many T distributions there are? Infinite number of T distributions. Okay. Each T distribution has different critical values. Why? Because it depends on the degrees of freedom. The degrees of freedom are what? How can we define the degrees of freedom? When we say degrees of freedom, we mean what?
The difference between total observation and the total number of restrictions.
The number of observations, let's call it n, minus the number of coefficients we estimate. So degrees of freedom is the number of observations that we have. So if I have 100 observations and I'm estimating 2 coefficients, my degrees of freedom are going to be 98. Okay. So it's the number of observations, 100 minus degrees of freedom, it's going to be 98. 100 minus 2. Okay, so this is the degrees of freedom. The critical values of the D distribution depend on the degrees of freedom. Okay, usually T distribution has, in absolute term, higher critical values than the normal. You can see, for example, 270 is greater than 2.75. 4.6 is greater than 2.75. So the critical values from the T are always higher than the critical values from the normal. Okay. Now, the other thing which is important is the second approach we talked about. The second approach we talked about is the confidence interval. What does the confidence interval include? The confidence interval includes all the likely values of a coefficient, of a parameter. Okay, so for example, you estimate the coefficient, let's say 0.93, and the 95% confidence interval is 0.75 to 1.09. What does this imply? This means that we are 95% confident that the interval contains the true but unknown parameter beta. So the minimum value beta can take is 0.77. The maximum value beta can take is 1.09, and on average beta is 0.93. Okay, so the confidence interval contains the minimum, the maximum, and the average value that beta can take. The minimum, the maximum, and the average value beta can take. The minimum, the maximum, and the average. Okay, and you would need to include this in your project as well. You need to include this in your project as well, confidence intervals. Usually confidence intervals are two-sided. Okay, how do you construct confidence intervals? Well, you're going to construct confidence intervals in the following way. You're going to calculate alpha hat, beta hat, and the standard errors. You choose the level of significance, for example, 5%, and the confidence interval is beta hat minus this product, beta hat plus this product. Okay, and the confidence intervals, I repeat, contains all the possible values of beta hat and the minimum value, the maximum value, and the average value of the two coefficients. Okay, the minimum, the maximum, and the average value of the coefficients. So these are the confidence intervals, and the tests of significance would always give you the same results. So they would always going to give you the same results. Always are going to give you the same results. That's why you would need to confirm this in your project. When you use the t-statistic, when you use the p-value, the results you're gonna get are going to be always the same. The results you're gonna get are always going to be, the conclusion you're gonna get is always going to be the same. Okay, so let's see an example. We have a regression where, in this case, alpha hat is 20.3, beta hat is 0.509, the standard error of alpha hat is 14.38, the standard error of beta hat is 0.25. Okay, so you can use the test of significance approach, and you can use the confidence interval approach. Who is going to tell me what is the t-statistic for alpha? Who is going to tell me what is the t-statistic for alpha? Who is going to tell me what is the t-statistic of alpha?
And 1.98
For alpha, what is in the numerator?
No, well, is 20.3 divided by 14.38.
Great. And the
The same for
t-statistic
beta.
So what is in the numerator? 0.591 divided by 0.2561. Okay. So this is the this is the t-statistic. Okay, this is the t-statistic for this, for the two coefficients. Okay, so the critical values for this specific case is minus 2.086 and 0.086. Where do I get this number from? Well, this depends on the degrees of freedom. So these numbers here depend on the degrees of freedom. Okay. So the test of significance approach gives me, well, here I'm not doing beta equals 0, I'm doing beta equals 1. So for beta equals 1, I get a t-statistic of minus 1.917. So I'm basically here. This is minus 1.917. All this region is what region? This is the non-rejection region. Okay, this is the non-rejection region. Okay, so what's the conclusion here? We do not reject since the test statistic lies within the non-rejection region. Okay, or in other words, you can say the absolute value, you can say 1.917 is less than 2.086. Okay, it's less than 20.6. I can do the same thing with the confidence interval, and the confidence interval would be beta hat, this is beta hat, plus minus 2.086. This is the critical value from the t-distribution. This is 2.086.